Pre-lab question 2 is always a bit of a doozy for people, and so I wanted to give you a walkthrough of how I would approach it. To read the problem, it says that we've got formic acid. Formic acid has this formula, HCOOH, and the actual molecular structure of it, the Lewis structure, looks like this. That's formic acid, and it can deprotonate, and when it equilibrates, it also forms formate, which is HCOO-. And formate, as you can imagine, is just losing the proton off of the formic acid. In this case, we are going to make a buffer. We're told that formic acid has a Ka that they give us, and they want to know how many milliliters of sodium formate, which is the base in this case, needs to be added to 20 milliliters of 0.1 molar formic acid in order to make a buffer with a pH of 3.4. So in order to solve that, what we're going to need to do is to use the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is the basic equation that you're going to use when you're calculating the pH of buffers. And we don't need to know the pH in this case. We'll be using it to solve for the volume of sodium formate, but the formula is going to look like this. pH of the buffer will be equal to the pKa of the acid plus the log of the concentration of the base, which in our case is HCOONA over HCOOH, the concentration of the acid. And both of these are at equilibrium. Now they told us the pH. They told us that was 3.4. But can we get the pKa from the value of Ka that they gave us? Sure. That's going to be the negative log of 1.8 times 10 to the negative fourth. We need to then solve for this ratio, and I'm just going to abbreviate and say the base is B, the acid is A. When you solve for this, it turns out to be 3.74. And if we bring that over to the other side, now we've got negative 0.34 equals the log of base concentration at equilibrium over acid. And we can get rid of this log term simply by saying 10 to the on both sides. So 10 to the negative 0.34, which is 0.453, is the decimal equivalent of this ratio of the concentrations at equilibrium. And what we're going to need to do is to figure out what are the concentrations of the base and acid at equilibrium. In order to do that, I think I'll remind us that this is actually kind of like an ice table. Now we'll have our formic acid. There we go, formic acid. And when it deprotonates, it can form formate. Initially, the concentration of formic acid was going to be, I think, 0.1 molar. That's right. And we had a certain volume of it. We had 20 milliliters. And then we have to divide by the total volume. We don't know what the total volume is. We just know that it's going to be the combination of acid plus base. We're not adding any protons in just yet, so I think what's interesting for us is that we have to focus on next the formate, the amount of formate that's present. So we've got 0.1 molar of that. We don't know how much that is. We're trying to solve for it. I'm just going to call it the volume of the base. It's going to be divided by the total amount as well. Now when you react this, formate in water is going to form hydroxide. And that hydroxide will react with formic acid. So it's going to consume some formic acid. We're going to lose this from both sides. And we'll be left with something that looks like this. I've just tried to simplify that a little bit. It just means that we're not left with as much formic acid as we started with. We used some of it up when we reacted it with the base. However, remember that when you react an acid with a base, the reaction is going to be forming the conjugate base, and in this case water. So we're actually reforming some formic acid, or formate in this case, and it will just be how much we actually reacted. So it's going to be 0.1 molar times VB over V total. These are the equilibrium expressions that we should plug back into our equation. So going back to this, we're going to plug these numbers in that we just got for the base and the acid. And we'll see that it's going to be 0.1 molar VB over V total divided by 0.1 molar times 0.02 minus VB over V total. Notice that the V totals are going to be the same. Those are going to cancel. The 0.1s are going to be the same. And so you're left with 0.453 will equal to the ratio of the volume of the base over 0.02, 20 milliliters minus the volume of the base. And that's how you would go about solving that problem. Good luck with it, and let teachers know in the open lab or your instructor if you have questions about how this is done.